Alrighty, in this video we are going to be talking about alternating series tests, and then the second video we'll talk about absolute convergence, and then in the third video we'll talk about alternating series error. So there are 3 videos for this lesson. It's going to be quite a big one, I would say. Anyways, up to this point we haven't really talked about anything that had alternating series. And essentially an alternating series is basically a series, but with a -1 to the power of n plop next to the series. So you can see how here I have -1 to the n minus 1, and then how here I have -1 to the n. Now, anytime you have an alternating series, we have a very easy test that we could use where we only have 2 conditions. The first condition is where you look at your sequence and see if that converges to 0. And then you also want to make sure that your terms are always decreasing. One important thing to note is that AST can never be proven to say that a series diverges. AST only can be proven that a series converges and only converges. If the 2 conditions are not met, then we'll probably have to do something else, whether it's a term test or a comparison using p-series. Now, one important thing about this is that you have to make sure that you write your conditions. And once you have verified your conditions, you have to make sure that you state your little template right here. This is going to be very important because from now on, I'm going to be pounding you guys with this statement right here. So we are going to say that the series is an alternating series whose terms decrease in absolute value to 0 and converges by the alternating series test. So that only happens whenever we know that the series converges. Up to now, here's the thing. Just like the integral test, you may or may not be asked to prove that the conditions hold. You might be asked to state the conditions, and that's fine, aka the terms decrease and the limit approaches 0. And if that's good, that's good. But sometimes you might be asked to prove that the conditions hold. So if they ask you to prove, then the first one is going to be taking the limit. That's going to be the easy one. And then the second one is going to be taking the derivative and seeing where our derivative is negative so that we know that it's always going to be decreasing. We'll do that for number 2 because number 2 is kind of special with that. But with number 1 here, I'm just going to state the conditions and then hope for the best in terms of it being true. So the first thing that I'm going to do with number 1 is look at my limit. And whenever I look at my limit here, I am only looking at the limit of my sequence. So the n over 10 to the n. So we have the limit as n approaches infinity of n to the 10 over n, and lucky for us, that's just 0. Now, do we know if the terms are decreasing? Well, if you just look at what's happening here, kind of looks like the terms are decreasing. So the limit approaches 0 and terms decreasing. Because those 2 conditions hold, then we could say that this right here, we're going to state the whole thing. So we're going to say this series, you actually want to write it out, so we write it out, is an alternating series whose terms decrease an absolute value to 0, therefore converges by the alternating series test. I know, that was a lot. That's probably going to take you guys like 30 seconds, but you have to do it. It's part of the conditions. All right, if we look at number 2 here, the first thing I'm going to do is go ahead and take my limit. So the limit as n approaches infinity of n squared over n cubed plus 4. Like for us, the denominator grows faster, so my limit will approach 0. Now, this is the part where I'm going to ask you to prove that our function or our sequence actually decreases, because here's the thing about number 2, if I were to put this on Desmos. You are going to realize that if I put this on Desmos, 3rd power plus 4, that we kind of increase a little bit after 1. So notice how here's like 1, and then we're increasing. That's not good. Now, even though we are increasing a little bit, you'll notice that from 2 to infinity here, we're always decreasing. So even though we have one slight term that goes increasing, it really doesn't matter in terms of the sequence in the long run, essentially. So even though we are increasing at 1 to 2, from 2 to infinity, we are always decreasing. So that's going to be okay. So that's why for this one, I'm going to ask you guys to prove that the sequence here is always decreasing. So proving it just means taking the derivative, setting that thing equal to 0, and calling it a day. She's going to be messy, I know, because you have to use quotient rule, but at the end, everything should be okay. So we have low d high minus high d low all over low square. We're going to set this equal to 0. The good thing about this is that the denominator is always positive, because n cubed plus 4 square, that's always going to be positive. So I'm only going to be focusing on the top part right here, and I got to simplify that. And that's going to help us find our critical points. So we have 2n to the 4th. Actually, hold up. Before I do that, I'm going to factor out n. N cubed plus 4. N, well, 2 technically, 2 minus n, 3n squared. And then I am going to simplify. 2n cubed plus 8 minus 3n cubed. That's going to give me n. Negative n cubed plus 8. So then you could see that our two critical numbers are going to be 0 and 2. Now remember that we're going to plug in 1 into the derivative, and then 3. I'm not going to worry anything before 0 just because my sequence starts at 1 here. So from 1 here, that's going to be 1, negative 1, plus 8, which is going to be positive. So that kind of makes sense from our graph right here, that from 0 to 1, it's increasing. And then if I plug in something like 3, I'm going to have 3, and then negative 3 cubed plus 8. That's just going to be negative. So you can see that my terms are decreasing for x is greater than 2. So terms are decreasing. Because my limit of n squared over n cubed plus 4 is equal to 0 and my terms are decreasing, then we can go ahead and write our little statement that I'm just going to copy from number 1. and write that down here somewhere. Of course, you probably don't have space from the fact that we did all of the other stuff. Oops, we don't want to do that. But you do want to make sure that you have it somewhere so that you know that the series converges by the alternating series test. Don't draw an error like mine on the AP exam. Actually write out the series, please and thank you. Okay, if I look at number 3 here, I'm going to go ahead and first thing I'm going to do is take the limit. So the limit as n approaches infinity of 3n minus 1 and 2n plus 1 is equal to 3 over 2. We have a problem. This right here does not equal to 0, which means that we cannot use the alternating series test, meaning we have to use something else. In this case, remember back in day 2, we talked about the nth term test. So what we're going to do here is just look at this right here. And we already know that 3n minus 1 over 2n plus 1 has a limit of 3 over 2. But then, because we have this negative 1 to the n, my limit is going to oscillate from 3 over 2 and negative 3 over 2. Because my limit is going to be oscillating, this right here is going to diverge by the nth term test. Very sad. I know. All right, if I look at number 4 here, I am going to look at this and I'm going to take this limit right here. I have the limit as n approaches infinity of cosine of pi over n, and then n to the 3 over 4. Well, I have another problem with number 4. This here, cosine pi over n oscillates from negative 1 to 1. So technically, what I can do here is rewrite this as the limit as n approaches infinity of negative 1 to the n of n to the 3 over 4. Now, once again, AST is going to fail because my limit oscillates. I can't really use alternating series tests. So, because I can't use alternating series tests, I need to make sure that I look at my whole series. Just like how here I looked at my whole series for number 3 in terms of including negative 1 to the n. So, I'm going to include this negative 1 to the n. And then this negative 1 to the n that we rewrote with the cosine pi times n. And that right here is essentially going to be the same thing as the limit as n approaches infinity of 1 to the n to the 3/4. These two just becomes negative 1 to the 2n, and the negative 1 squared becomes 1. So we get 1 to the n, which is just 1. And then based off of this information, you could see that this is a p-series. And unfortunately, because this is less than 1, I can't really do much here. So this here is going to be diverges by p-series tests since 3/4 is less than 1. All right, same thing with number 5 and number 6. The problem is with number 5 and number 6, we actually got to figure out what the formula is. Now, notice how for number 5, we have a positive term first. So whenever I do n is equal to 1, I'm probably going to do negative 1 to the n plus 1. Just so that this right here, whenever I plug in 1, I'm going to get a positive answer. You'll also notice that the top part is always 4. And then you'll also notice that if I have 7 here, then 7, 8, 9, 10, 11, then I'm probably going to do n plus 6. So that my first term is 1, well, 7, so that 1 plus 6 is going to give us 7, 2 plus 6 is going to give us 8, and so forth. All right, so once we do that, we're going to go ahead and think about the limit as n approaches infinity of my sequence of 4 over n plus 6. Lucky for us, that's just going to be 0. And then what we're going to do here is look and see if the terms are decreasing. What I'm going to do is just take the derivative because I think that's going to be easier. Lucky for us, that's just going to be negative 4 n plus 6 squared, and then at negative 6, we can make our little thing, because that's my critical point, that's where it's undefined, but you'll see that it's always negative anyways, so this means that my terms are always decreasing. Because these two work, then we are going to say that this series right here is an alternating series whose terms decrease in absolute value to 0, therefore converges by the alternating series test. Of course, write out the alternating series test, don't abbreviate AST, write out alternating series test. All right, looking at number 6 here, what we're going to do here is think, okay, I have a negative first. So I am not going to do any plus 1s. I'm just going to do negative 1 to the n, because if I do negative 1 to the n here, that's going to give me negative 1 to the 1, which is going to give me a negative starting point. My top here, notice how it's all even, so that's just going to be 2n. And then my bottom here, I'm going up by 1, but since I'm starting at 5, that means that I have to have an n plus 4. All right, so then we have the limit as n approaches infinity of 2n over n plus 4, which is 2, and that's not 0, so we can't really use AST, meaning that we have to use nth term test. In this case, that works because the limit is 2, well, it's oscillating with negative 2 and 2. So this right here, because my limit oscillates from 2 and negative 2, therefore, so we know that the limit diverges, right? Now, you still have to tell me that the series diverges. So you can't just say that the limit diverges and call it a day. Hopefully I didn't do that for the other one. Oh, I did. Oops. I forgot to mention. You want to make sure that you specifically tell me that the series and not the limit diverges, because the question is talking about the series. So that diverges by nth term test. This diverges by p-series test. And then this right here, not the limit, but the series, diverges by nth term test, because we know that the limit diverges. All right, and the next part, we're going to talk about absolute convergence, which is essentially more on alternating series, except this time we'll see what happens when we put an absolute value with convergence.